really silly. Yeah.
So Jitendra, I agree with your critiques, but your focus on imitation is a little bit theistic. You believe in this father figure that is going to tell the world how to act. But how did this happen in the first place? Allison argues that most of learning in babies happens self-supervisedly, not.
Yeah. No. I was not trying to be exclusionary here. I always give one example. When somebody says everything is learning from others, I always give the example of crawling. So a baby learns to crawl, and they usually don't see their parents crawling. So clearly that is driven by something else, right? So there's a lot which is not cultural transmission, but you need to have a theory which allows for cultural transmission. So I think there is a role for imitation learning. There's also a role for self-based stuff, because otherwise how would we discover new stuff? I mean, if you only had cultural transmission, we would still be hunter-gatherers, and we are not hunter-gatherers. Okay, I think Shiri is going to kick me out now.
Why don't you take Robert as well, because we'll try
Oh, okay. An outsider's question. It sounds like, but is it, that what you're saying is basically that Rodney Brooks was right, more than 30 years ago, that the constraint on progress in AI is a division between so-called sort of peripherals, the sensory input, the effectors, and a central representational device, and that the effectors and receptors are intrinsically need to be seen as a part of the cognitive system rather than just input and output devices. That seems to be like the way that you're going with this, but do you think that also, what are the implications of that for disembodied AI?
Yeah, no, so Rod Brooks and I are very much in the same camp. I mean, we were grad students together, we had the same advisor. So philosophically, this is not so far apart. Okay, and I'm very much an embodiment person. So I can't give the arguments for the people who believe in disembodied AI. You have to find others.
Okay, thank you very much. Okay, next we have Misha Tsodyks from the Weizmann Institute.
Okay, thank you, Shiri, for the invitation. I actually have a group that is divided between two institutions, the Institute for Advanced Study and the Weizmann Institute. And I'll present a project that about human memory that was a completely new field for me until I met Mike Kahana, who is a famous psychologist at UPenn, who introduced me to this field. So, studying human memory developed along two basic kind of directions, and all of them are quite old now and have a foundational kind of people, Ebbinghaus and Bartlett, respectively, and each one wrote a book which is very influential in the field. So Ebbinghaus introduced studying memory based with using kind of list of nonsense type of material, because he thought that if you strip the memory from all the meaning, you can actually get to the basics of memory and discover some foundations. And Bartlett, on the other hand, introduced the idea that studying memory with nonsense material is nonsense, because the most interesting thing about memory is actually to relate it to comprehension and cultural backgrounds, etc. So it couldn't be more different than these two lines. So I made my way from the nonsense materials to meaningful materials like that. So I will very briefly talk about this one, mostly to kind of make some more generic statement about what the modeling of this phenomena could really be, but most of the talk will be about narratives and implications for language, etc. So this is a very quantitative field. People studied this for many years and discovered really a lot of interesting basic phenomena. Most of this you may even know, even though if you are not from the field. So you know what primacy is, that you're easier to remember things at the beginning of the list. So, for example, you probably all remember Jack Gallant's talk because he was the first at the conference. That's a primacy effect. But there is also recency effect. There are a lot of other effects. For example, if you present this list with a faster or slower, this has a very strong effect on the memory, and that's true in real life. When I hear somebody speaks very fast, I have a hard time remembering anything, but people who speak slower, for me, it's much easier to remember. Obviously, it depends on the age of the participant. Younger guys have better memory. A lot of interesting and fundamental observations. So now the question is, what would it mean? And I want to really spend a little bit of time on this issue. If you want to have a model of this, and you want really to strive to have a good and correct model, not just one of many, many models, what would it take? Would you want to include all of these observations into your model? Well, that's how psychologists go about it. So they have very complex models, and every time a new phenomenon is discovered, they put it into the model. And then everything that Jack said about the models in biology applies. So none of the models are correct, all of them are wrong, and very rarely people go beyond the observations that they themselves measured. So they have a model, they reproduce the observation, say, great, that's a correct model, even though there are many other models that may explain these observations equally well. So the whole notion of correct, wrong, useful models is a bit muggy here. On the other hand, because I'm a physicist by training, so for me this is like a very messy thing to do. Physics succeeded not because the world is simple. The world is very complicated, but physics succeeded because physicists know how to extract the fundamental things that they want to model and ignore things that not. Let's take an example of Newton. Newton wanted to explain the rotations of planets around the star, the sun. And he had a theory. Was his theory correct or not? Well, it's a strange question. Everybody will say, of course, it's a correct theory. On the other hand, judging by the standards of psychological style of modeling, his model was wrong. So there are a lot of things about Earth rotating around the star, the sun, that this model doesn't explain. It doesn't explain that the Earth rotates around its axis, that there is a winter, that there is summer, that the temperatures change according to every day. So Newton didn't want to model all this. If he would try to include all of this into this model, we would not have physics now, right? Because there is no way he could come up with this. So you could try. I think my point is that biology is complicated, and the world is also, the material world is no less complicated. The question is, can you really find some fundamental things that you want to model in biology at the expense of others that you may put aside? So what's the fundamental thing about this phenomenon on the how people recall lists? There is one basic observation is that people recall fewer words than they can recognize. So if I give you a list of, let's say, 20 words and ask you to recall them, you may recall like around 10, let's say. But if I show you a word, you'll recognize every one of them. So there are 10 more words that you remember, but you cannot recall. And I say, maybe let's try to see how this can come about. Why you cannot recall all the words that you actually remember. And so very briefly, I came up at some point with a simple idea. And the idea is like that. So because it's completely random set of words, there is no meaning to this kind of list. So you can imagine that every word is encoded in your brain by a certain pattern of activity, and the correlations between these patterns are random. They're not meaningful in any way. So when you recall the words, you make transitions between the words based on these correlations between the encoding. So you basically have a map which you see in this graph. So every word is mapped into another word. And this map is deterministic. It's determined by your experience with the words. But it's random. If you take many different lists and many different people, these arrows will be randomly distributed across this graph. So now, if you just follow these arrows and see how you recall the words, you will recall some number of words, and then you enter into the loop. And because I assume the map is deterministic and the process is deterministic, you will never get out of this loop. So in this case, out of I think 16 nodes in this graph, this trajectory visits 7, and the others are never visited. Right? So that's a model, that's an idea of how I want to explain that people recall fewer words than they remember. Right? So you have 16 recognized words, I call it M, and 7 recalled words, I call it R. And I want to understand the relation between these. I want to understand why R is less than M, and well, I understood already how R is less than M, but I want to predict R from M. Now, I cannot exactly predict R from M because it's a random graph, but I can predict the statistics. I say if you have a lot of graphs of the same size, M, and you put these arrows at random, what's the statistics of R? For example, what's the average R? Turns out you can solve this problem. It's a mathematically solvable problem. And you get this simple relation. So R, on average length of these trajectories, grows as square root of M with a precise prefactor. What does it tell us? So if this model is correct, it means that if you measure both M and R, if you do experiments where you measure M's and you measure R's, and you try to relate one to another, you should get this relation, which is totally universal, right? There's no freedom, there are no free parameters that I can fit to the data. So the data either confirms it or refutes, right? And nobody ever did this this analysis, because people usually measure recalls and they try to see how it depends, let's say, on the number of words in the list. I'm saying that's not the right thing to do, because there are a lot of manipulations that will change the results. But if this theory is correct, no matter what manipulations you do, both R and M will be affected by these manipulations, but the relation between R and M will be the same. So you can present the list with a high speed, low speed. You can take young people, old people. Whatever you do, you don't even have to present words. You can present some other things. You should get this relation. So we wanted to test this. So exactly at this moment, you could now do experiments with the internet platform. So I didn't have to ask my psychology friends to do this.
Where did that equation come from?
It's just a simple. I cannot tell it now. You know, it's a mathematical solution of this random map problem. And we did the experiment. So we had, you need a large number of participants, because this is the statistical results. You need as many manipulations as you want, because you want to prove that no matter manipulation, you get this relation. And believe it or not, we have this result. So we did manipulations that we did is that we took lists very short or very long, up to 500 words in them. We presented them with different speeds. We then replaced words by short sentences. And all these manipulations that we did, all the data points that we have, were very close to this curve. I remember still the face of a student, Michelangelo Naim, who at some point when he put it together and came to me, was in the Santa Barbara program in 2019 that I directed together with Tatiana. I don't know if she remembers this program. And he told me, Misha, I just can't believe it, but you know, all our data, if you plot it in the right way, it's exactly on this curve. Okay, so this was I was obviously very happy about this, but on the other hand, this is a kind of esoteric problem, right? Who cares about how we remember random lists? In real life, nothing is truly random. Things are, much more complicated than that. And so this is much more interesting problem now. You have these narratives. So we have a set of narratives that to play with. This is a famous linguist in Columbia that studied narratives in the 60s. So he just asked people to tell him what are the dramatic experiences in their lives. And so he observed that when people speak to a linguist, they're usually like very shy and don't speak in a natural way. But if you ask them to tell about something dramatic, they forget about everything and they start speaking normally. So that's why he chose this idea. So he collected a set of narratives like this, of different lengths. Some of them are very short. This is a very short one about a guy who was in the Boy Scout and almost drowned because he got cramps when they were swimming, but was saved at the last moment by some passersby. And some stories are much longer. And the question is, can you do something similar to what we did with the list to this thing? Now, that's much more complicated thing. When you read this story, you are not, you read it as a sequence of sentences, obviously. But, you have a whole world in your mind when you comprehend the story. You like, this episode in the life of the narrator becomes like part of your life now. You know what happened to him, you have emotions, you have everything. So when you recall this story, you are not recalling it sentence by sentence. Not, of course, not word by word, but not even sentence by sentence. You have this experience in your mind, and you now retell the experience. And that's much more complicated, but much more relevant to like how we really understand things around us, how language is constructed. So I think if you really understand well how people recall the story, you understand a lot about language and about cognition, about comprehension, etc. And this was the point of Bartlett. That's why Bartlett was so much against quantitative analysis of this experiment, because he said it's just impossible. It's like as if you want to basically understand the human mind with equations. Okay, so how do you start? There is not much data. I mean, people do experiments, but these experiments are done in a very, for few subjects, usually isolated stories. Each story is unique. Each subject is unique. If you want to find any statistical regularities of this, you need a different approach. So again, having platforms now makes it possible. So we had chose a set of lab of narratives with a range of length from like 19 to 190 short sentences. And we have 100 subjects per narrative. You really need a lot of subjects because you read how people recall these stories. It's extremely diverse. Right? So what is this? Yeah.
They're not telling a story.
So we have, these stories were told in 1960s. They were annotated by Labov. We now choose go to prolific. We have subjects of prolific. They sit in front of the computers. We put the story sentence by sentence on the screen, and then they type the recalls. So we collect the recalls. That's our data. So what do you see if you read the stories? Like, it's a whole world. I cannot describe it in a minute. But what's the most fundamental thing? How is this recalls differ from recalls of random lists? Well, I think the most important difference is that if you comprehend the story, if you know the story well, it becomes like a part of your experience. When you retell it, you don't necessarily repeat like every detail from the story, obviously, right? You don't remember all the details, but even if you did, you don't necessarily want to do it. You want to recreate this experience for another listener, for the listener, as much as you want. So you may compress pieces, like some pieces you may compress and say something. You can infer things that were not in the story. So I think the most fundamental way the recall of meaningful information differs from this nonsense material is this abstractive summarizations. It's called an LLP, or it's basically some compression. So here is a chunk of the piece of the story about how the other guys in the Boy Scout and the Scoutmaster didn't believe when the character started yelling for help. And so he started going down. Okay, so this is a bunch of sentences. you don't have to repeat all of this sentence. You just have to say, I was left behind to drown. And this will be very good, right? Because for the purpose of the story, this one sentence communicates everything that you want to know from here. And this could be much more radical, right? So this is a very, very long story where there is a long episode about how people came to police to complain, and somebody recalled it with just one sentence. So there was some type of altercation, and the police were involved, okay? And this is fine. This was a good recall, because this whole thing was recalled as one sentence, but it was coherent with the rest of the recall, so this is actually a fine thing.
How do you decide that it's fine?
I'm just saying subjectively. If you read the recall, you see it's a very coherent recall, and you get an idea what happened in the story well. You didn't omit anything crucial. If you omit something crucial, some of the recalls are incoherent. You don't really know what happened. But this recall was quite okay. So based on this observation, so let's just go with this basic thing. I say that's a major fact about recalling this story, this compression, so summarization. And my main hypothesis now based on this is that when you comprehend the story and you store it in your memory, you don't store it as a sequence of sentences. You store it as these summarizations. You do these summarizations all the time. Like when you read the story, you summarize for yourself what actually happened. You make a tree out of these summarizations because these main key points, I would say, are related hierarchically to each other. And that's what you have in memory after you read the story. Okay? So let me give you an example. So if you go from down to up, this is the part of the original story about this episode. So the fellows didn't believe the guy, then the scoutmaster didn't believe the guy, and so he started drowning. This is 8 sentences. This are naturally divided into 3 chunks. Each chunk can be summarized by 1 sentence. The other boys didn't believe the narrator. Scoutmaster didn't pay attention. Narrator began to drown. But you can go further and summarize it into 1 main key point, saying the narrator was left behind to drown. Okay? So based on this thing, I say that all of this is now in your memory when you comprehend the story. So that's why you can easily retrieve any of this. Depending on how much you want to tell me about the story, you can just say 1 sentence and more sentences if you still remember. So you have a tree. So this is an example of a tree. You have a story of 42 sentences, which is divided into a set of 4 big chunks. So every chunk communicates 1 particular key point. And then you just recursively divide it more and more until you are left with a single sentence. This doesn't have to be the full story, because some of the story you may forget or may not integrate into the thing. But this is some kind of subset of the story that you now compress, represent by this tree. So that's assumption number 1. Now, in order to this tree is very individual, right? The same people reading the same story, you have different trees because they understand stories differently. And of course, if you have different stories, you have different trees. So the word random here means like a random map in the model for the nonsense recall, is that I'm making an assumption that if you consider the many different stories of a particular size or many different trees, they will look like a random collection of trees, which means that, for example, the division of every piece into chunks will be random. Now, you see there is this 42 sentences were divided into 4, 3, 27, 8. But in another story where there are 42 sentences, this would be a different division. Right? So just put, so the only parameter for this ensemble then is how many chunks you have. What's the splitting ratio? Like what's the maximal number of children that every node in this tree has? So in this case, it's 4. That's assumption number 1. Now, what do you do then when you recall? So you have this tree. And the second main assumption is that when you recall the story, you have to go from the main idea down to a particular level, and you have to keep in mind all of these intermediate key points, because otherwise you will lose track of where you are. If you want to recall the story in a smooth, coherent way, you have to, every time you have to keep track of where you are in the story, which branch you belong to. So this means that you have to remember at any moment I can stop you and ask you where you are in the story, and you say, yeah, I'm talking about this particular episode. So this means that you cannot go too down into the tree. If the story is very, very long, the tree is very deep. Or you cannot go down. Even if you remember some of these details, you cannot go too down because you will lose track of where you are. So there is a lowest level to which you can go down. So, and then you go to this level, and then you just read out everything that you have in your tree at this level. So you have this many sentences, and you recall, and you will say that the first sentence is an individual one. This summarizes 2 sentences, and you will have this kind of degrees of compressions that correspond to this layer. And if the tree is very big, then of course you compress more and more, which is obviously what you see in mine. Now you have these 2 parameters, the splitting and the largest depth. And when we started thinking about it, I just made a leap of faith. I say both of them, I don't want to treat them as free parameters because in my view they're related to the working memory capacity, how many chunks you can keep in mind simultaneously. And so I just made a assumption before we looked at any data that both the D and K should be 4. So if you believe in this logic that it's all related to working memory capacity, again, you have a model that has no degrees of freedom anymore, right? If you tell me what's the size of the tree, I can tell you exactly how many nodes there are at any layer and what are the statistics of these summarizations or compression levels. So there is an analytical solution to this problem. If you tell me what's the size of the tree N, how many nodes there are overall, and for every layer D, I know how many non-empty nodes there are. And this is the equation, and this is the graph. It's not as nice as, there's no square root or exponential. It's not an analytical formula, but it's still an exact solution. And that's how it looks. So if you increase N, obviously the number of nodes at any layer is increasing, but it's increasing very, very slowly, and it cannot cross the asymptote, because if the tree becomes very, very big, you just fill up completely all the nodes. And so in the case of K equal D equal 4, there is an asymptote at 64 where these curves cannot cross. So I have if you really believe in this, I have a very strong prediction now that on average, no matter how long the story will be, the recalls will never go above this number 64. And you can also calculate the distribution of these compression ratios. And this is very much like a place field distribution. The reason I want to show it is that for Tatiana to see it. She showed the distribution of place cell sizes. And this is like a place cell, because every sentence represents a piece of the story, right? And so if you have a very high compression, this is a sentence that is like a large place field. If you have a sentence that communicates a single sentence of the story, it's like a very short. And you have these distributions which maybe look similar to place field distribution, but you have to look at it. Okay, so now we have data. So what do we have with the data? You have the stories of different lengths. And the model kind of informs how to look at the data. What do you want to measure in the data? And surprisingly enough, nobody looked at the length of the recall. People look at all sorts of very complicated things about the recall. Nobody had an idea just to look at how long the recall is as a function of this story length. So this is what the model kind of encourages you to do. So if you do this, if you average the recall length for this story that you have, and you see there is a very, a kind of a simple curve here. It's a very, very smooth curve if you average enough. And it looks qualitatively very much like the model predicts. It saturates very quick, doesn't grow proportionally to the story length. So the only thing that's missing if I want to compare it quantitatively is, again, I want to relate the story length to the size of the tree. I'm not expecting that the whole story is incorporated in the tree. So here, where you can use LLMs to connect one to another, what you can do is you have a story, you have a particular recall. you do the map. You map every recall sentence into the story using some prompts. And then you find that, let's say, every sentence will be mapped into different number of sentences in the story. So this would be how you measure the compression ratios. But you can also see that some of the sentences in the narrative are not mapped into at all. So they're like holes here. So if you just count how many sentences from the story are mapped into, you know what part of the story this recall actually summarizes or reflects.
Measure the degree of similarity between sentences?
I'm not measuring anything. I ask LLM to do the map. 2 minutes, I'm almost done. So now we have an N for every story, for every subject. So you can look at how this relates to the length of the story. It turns out that people, on average, summarize about half of the story. So no matter whether the story is short or long, I don't know why this is. So this is just empirical observation. But now we have the size of the tree for every story. You can now overlay experimental data on our theoretical prediction. Again, I have no freedom to change anything in the model because I decided in advance what the parameters is. And I have a great performance, right? So again, made me very happy. If you look at the compression ratios, it's qualitatively okay. It's not as good. If you look, sometimes you have deviation, but the trend is very good. Right? The story gets longer, the histogram shifts, there are more and more compressions. I have 1 minute. Okay, now you have this idea which I think captures the fundamental aspect of how people comprehend and recall the stories. Is it the right model or not? So like if Jack will ask me, how do you know it's a right model? I would say, I think it's fundamentally right because it reproduced a very non-trivial effect with a very minimal number of assumptions. But can you really go and more directly prove it? Well, one way to try to do it is to really chunk the stories into pieces and see what do you get. So now, again, it would be very difficult to do it manually, but with LLMs, you just give LLM a bunch of stories of different lengths, and just do recursive chunking by dividing every chunk into up to k subchunks. So you get trees like that. And now you can see what's the statistics of these chunk sizes. So you see it's kind of looks random, but how random really it is. How close it is to our random tree ensemble. Turns out that if you choose k correctly, you have a quite good match, right? So there are kind of distributions of chunk sizes at every layer is not so different from the model. But moreover, you can ask what's the right k to do. And again, surprisingly, you see that for the stories of this type, like general purpose, like general kind of Reddit type stories, if you repeat this chunking procedure for different Ks and ask when your statistics of chunk sizes is most similar to the statistics of the random splitting sizes, you get that K equal 4 gives you a best match. Okay, so there is kind of independent confirmation that the random tree ensemble describes the structure of the stories pretty well, and k equal 4 is actually the correct number. Okay, and in 20 more seconds, I can tell you that there is a whole new direction where you can try to understand the entropy rate of English. Entropy rate of English is a very classical problem that Shannon initiated. He had some initial experiments to estimate how much information every word in the story, in the language carries. It's about between 2 and 3 nuts per word. That's what he measured using human participants. You can now calculate the entropy rate of the trees, and then I'm not going to explain how we do it. And you have this theoretical result that the entropy rate of this tree ensemble, just ignore this curve, is this blue curve, depends on the splitting factor k. And if you go to 4, you get the entropy rate of this tree ensemble very close to the empirical measure of information rate of English that Shannon calculated. We have these 3 lines of analysis and theories that kind of are really extremely consistent to each other, that one confirms the other one. So let me finish here. This is my conclusion. Yeah, thank you. Sure. Yes.
I was wondering, is Phil here? Phil's here. I was wondering, so Phil was talking about memory the first day, and you were talking about memory now. And if I recall correctly and summarize what you said, I think that talk was more about what do I remember? And this is a different mechanism,
How much?
way of summary, right?
How much,
The
yeah.
mechanism here is summarization. And I was wondering, maybe for both of you, how do these two things relate, like, to each other?
Well, like in general, if you ask me what people remember from a given story, I cannot tell, right? And it's impossible because different people will recall it. I can say it's not completely random. I can say in the given story, particular pieces are more important for the story, right? I can ignore the rest, and it would still make a story. Other pieces are not coherent, right? If you ignore the important things, this will become like a random thing. So people obviously are very good at identifying the right things. So this theory that I develop here is kind of orthogonal to this, right? I'm not telling you, I'm not trying to predict, like you give me a story, I'm not trying to predict which pieces of the story are more important than the others. I'm just saying that statistically, the distribution of these sizes is following this statistic that I hypothesize, basically, and it gives me a correct prediction for let's say, the length of the recall. So it's a really orthogonal approach. I'm not saying, obviously it's very interesting to try to understand exactly how people comprehend the story and why the different pieces are more important than the others. But that's just not what I'm doing. It's much more complicated.
I think the surprising parts are easier to remember. You have surprising parts
Right.
of the story. They're probably less predictable by the LLM.
Right.
Those would probably be more memorable.
Yeah. Yeah, it's a very complicated relation because there is things in the story that are completely uninformative. For example, in this story about the Boy Scout guy, there is the last sentence, the two last sentences were that some random guy jumped over and saved me. Like everybody you ask will guess what the last sentence will be. Because the whole thing is developing in such a way, obviously you know that since the guy is telling the story that he was saved by the guy. So it has zero information, semantic information, if you calculate it, has zero semantic information, completely irrelevant sentence. On the other hand, everybody, all the people, when they write the recall, they put the sentence in because this makes the story kind of complete. So understanding why people assign such an importance to this sentence is a very non-trivial thing. So I have actually had no reasonable answer to this question. Yes.
Yeah, maybe just there might be a lot of interesting connections, but I want to point out that in my talk, I didn't say anything, I didn't connect any empirical data about humans, I didn't actually answer what humans remember, it's just a machine learning algorithm. But I'd like to give the call to arms that it would be really interesting, I think, to take RNNs of the kind we trained or other kinds and actually ask, are they good models of human memory?
Okay.
They
And also LLMs. We're doing it now with LLM, but
Yeah.
I will be happy to try RNNs.
So I don't know. Yeah.
Yeah, please.
I wonder if you've thought about mathematicians, sometimes their proofs are short, sometimes they're very long. If you've done anything like this to see what they remember.
About the proofs.
Yeah, they can reconstruct the whole proof, but initially, what is it that they...
I didn't think of it, but now introspectively, I studied a lot of math in school. And obviously, if you think about the complex theorem that you're proving, you can summarize, there are like major milestones in the proofs, and then you just go down. So I think this could apply potentially to this, like at least theorem provings or any theory. Like if you talk about calculus, again, you can summarize it in few sentences, but then each sentence will have a lot of uploading to do. So, yeah.
It's a really cool talk, Misha.
Thank you.
In Vision, there's a old, like, theoretical history of optimal coding theory, trying to basically explain a lot of biological observations about vision in terms of the statistical distribution of images. And it seems like this is almost kind of an optimal coding theory for language.
Yeah, I agree, but I cannot prove that it's optimal. I didn't do it, but maybe with Tatiana's, who just left, but because she's claiming that this kind of distribution of, let's say, place field sizes is not just out of nowhere, right? It's an optimal way to represent the space. So it could be that this is the optimal way to communicate the story, but I cannot prove it now. I don't know even how to approach it, but I want to collaborate with her about it. Yes, Adarsh.
You mentioned that you also have some evidence for other type of data, like images.
No,
Oh, okay.
but I want to.
I see.
I want to, yeah. I was talking
I
to
think that
Simon
would
a
be very
bit about it, because if you look at the complex picture, it's like you're reading a story.
Yeah.
And there are things that you can do with it that you cannot do with the stories. So
And there is a lot of data, like Oliver, for example, has collected a lot of this kind of data, so you might just be able to.
well, this I
Plug it
would
in.
like to know, yeah, if you can, yeah, maybe we can chat about it.
Well, it's different.
Yeah, please.
I was going to make
Let's
the
do
same.
you do it.
Okay, you too.
No, so I have done work on images and segmentations, you also get trees, right? Because if a human divides up an object or a scene, they divide up into objects, and then objects are into parts. Different people will, so they construct trees, but the trees will be of varying levels of depth for different people. So,
Yeah. Yeah.
we didn't analyze it this way, but it might be interesting.
Okay, that's interesting. The way I thought about the picture as a tree is that you have a gist. I mean, it's kind of complementary problem, but you are saying that spatially it's like a tree, you segment it.
Yeah,
But
it is a
also, if you
pathology.
want to understand what's behind this, the picture, what actually is the story behind, it will have the same as the tree as a story. Like you have a gist of the picture, what happens there in one sentence, but then you can explain it more and more. And I don't know how it's related, but it may be related one day. Yes.
So you have a tree as a representation, and
Yeah.
one of the particular aspects of a tree is that it will tessellate the space in such a way that you will not be going from nodes which are children of one parent node to a different parent node.
Yeah.
So have you looked at how semantically people may be recalling things from these nodes into the other node?
Yeah, that's a good point. I mean, obviously, this is a simplification. The real stories are not trees. So the model is wrong right away, because you may have a story where the first sentence is directly connected to the last sentence, even though they belong to different chunks. Obviously, I ignored a lot of things, but I'm saying in the stories, at least like that, where there are no flashbacks and no kind of complicated twists, the narratives really go like as the actual experience developed. And then the tree is a good approximation. For other types of stories, maybe it will not be a good approximation. If you look at Pulp Fiction, probably this will not work. But you'll have to think about how to segment it differently.
Thank you very much.
Thank you.
Okay, if you are a student or a postdoc that's giving a talk this afternoon in the lightning talks, I need you here now. Everybody else, we will break for lunch. We'll come back at 1:30. We're going to start with Paul